Hello everyone. So in this video we'll discuss about one of the most important topics in digital electronics, which is finite state machines or FSM. So from the name itself it is evident what do we mean by FSM. FSM means you are representing a complex system with help of finite states. Let's say there is a system. Let me take an example that there is a system where you need to unlock your phone using a pin. There is a 3-digit pin and you need to unlock your phone by entering the pin. So how do I model this as an FSM? First, what will be the state of your this function in order to perform this functionality? The first state will be my phone will now give me three spaces to fill up where you need to enter the pin. So the pin value is entered here. Now that inside my phone, I already have my golden password, which is my correct pin, the golden pin, and this is the entered pin. So it will now map the golden pin with the help of this input which I have given, and then it will check whether this is a correct pin or not. If it is correct pin, if this is correct pin, then you will unlock the phone. And if this is not the correct pin, then it will again give you two more attempts. So within those two more attempts, if you are able to figure out the correct pin, then you will move on to unlock stage. Within those two attempts, if the number of attempts is less than 3, that means this was the first attempt and these are the uh, remaining two attempts. Out of these two attempts, if you are able to figure out, then the phone will again unlock. If you are not able to figure out the pin using the remaining two attempts, then it will go to move to a new state where you lock the phone for, let's say, 5 minutes, or you raise an alarm. So this functionality was depicted with the help of finite states, and that is how FSM comes into picture. So FSM helps you to represent a very complex system or a very complex functionality into finite states in a very compact manner. The second example I would like to take is for a RISC-V CPU. In a RISC-V CPU, in a multi-cycle CPU, there are many stages. So in a CPU processor, what happens? There is a machine code. The machine code is nothing but your instruction. So that machine code instruction is given to your CPU. The CPU fetches this instruction. The instruction is given as an input to the CPU. This stage is nothing but the fetch state. After the instruction is fetched, from those instruction, which is nothing but binary zeros and ones, from those instruction there is a decode logic. Now the decode stage will come. In this decode stage, what will you do? You will figure out what is the instruction trying to tell me. What should I perform using the CPU in order to fulfill or in order to implement this instruction. So let's say this instruction tells me to add R1 and R2 and place the result in R3. So I'm taking the value from R1, I'm taking the value from R2, and I'm placing the result in R3. So this is not represented in binaries in your machine code. So that is fetched, and then you decode this instruction. That is, you figure out what is the my source register, what is my destination register. That is your decode stage. Then you perform the execution. So in your execute stage, we are performing the addition of the value present in R1 and R2, and then you are storing the value in R3. So similarly, this entire sequence, after this execute stage, you write back the result to your destination register, which is nothing but R3. So you have seen that similar to this add instruction, there are multiple other instructions. There is load instruction, there are store instructions. So for a CPU to perform all these instructions, you need control signals. And what do I mean by control signals? Control signals meaning whenever you want to perform this execute stage, what are we doing in this execute stage? In execute stage, I'm saying that whatever value is there in R1 and whatever value is there in R2, I need to add these R1 and R2 to perform I need to perform this addition. I need to store this ALU result. This is happening in the execute stage. So this ALU must understand that the value that is coming from my R1 and value that is coming from my R2 has to be added. So for that addition, there should be some control signals that tells my ALU that addition has to be performed. Similarly, for every stage, there are certain control signals that have to be asserted or deasserted, or those control signals will take up some values so that you are able to perform your required functionality in every state. So this control signals and this entire functionality is represented in form of an FSM. This FSM compactly represents your multi-cycle RISC-V CPU. So FSM is not constrained to your sequence detection that we study in our BTech. It is extended to huge complex systems. So complex systems which so this FSM helps you to understand how these complex systems behave in a very easy manner. In one picture itself, we can figure out how my system is behaving, how my control signals are asserted. So this is a best way to represent a system. Next, we will move on to what are the different types of FSM that are present. So this is the classic images which we find in any digital electronics textbook to showcase what is your Mealy type machine and what is a Moore type machine. So we have studied that Mealy, we already know that by definitions the Mealy type machine depends on your inputs as well as the present state value. So in order to determine what is your next state, your outputs of your next state, in order to determine what is your next state and what will be the outputs of this next state, you need to have the information of your current state as well as the inputs of your uh, inputs that are given to the combinational logic. Whatever inputs you are giving and whatever state that you are presently are the determining factors for your next state. Because this is important because let's say you have a vending machine. So in vending machine, your next state, in order to determine whether your the item will be given to the customer or not, you need to have this information that how much money was inserted in the previous state. So previous state information is a very important determining factor to figure out what will be the next state. Okay, so this not only depends on your previous state, since at every clock edge your state will change. That's why you need memory elements to store the present state. All the present state information will be stored, but in the next stage, since there will be a loss of information, that's why you need memory elements. So it holds the present state and it gives you the input values based on which you figure out the next state. So this is not only depending on the clock, but it is also asynchronously depending on the inputs, because if your input will change, your output will also change. It will not wait for the next clock edge to arrive. As soon as your inputs are changing, your outputs will also change. So there is a possibility that it might asynchronously change with the inputs. It does not only depend on your previous state. Similarly, you have the Moore type machine where your inputs are given to the combinational logic and your present state is also given as an input to the combinational logic. So you hold the present state and only this present state alone is given as an input to your next state. In order to figure out the next state, the outputs of the next state, you only need your present state. And then without any requirement of the inputs. This means that this next state will be figured out at every clock edge. Even if your inputs are changing, that won't have any effect on your next state, because your next state at every clock edge only your next state will change based on the present state. Okay, that is the difference in Mealy and Moore. So by definition itself, we can say that Mealy is faster because as soon as your inputs are changing, your outputs are also changing. So definitely this is faster, but this will always wait for a clock edge, or this will wait for your present state to figure out the next state. So as soon as irrespective of your inputs, your state won't change. So this is comparatively slower, and we will later look at that Moore will have more number of states compared to Mealy. So based on your requirements, whether you need more states or whether you need less states or whether you need a dependence on the inputs or not, you decide whether you have to go with a Moore type machine or a Mealy type machine. For example, if you take a look at this RISC-V multi-cycle CPU, this is an example of a Moore type machine because your state is not dependent on the inputs. Your state your next state is determined at every clock edge. At every clock edge, your CPU comes to a new state and there is no dependence on the inputs for it. In order to determine the next state, you don't need the inputs from the previous state. You solely at every clock edge, you change your state to a new state value and accordingly you change your control signals. Okay. Before proceeding with the sequence detection, let us understand few things. So this is the Moore type FSM and this is the Mealy type FSM. From visually we can figure out the number of states in Moore is more than Mealy. Why? Because the output is dependent on the state. So for every state S0, S1, S2, S3 there is an output slash then output is written here. So for every state there is an output even though your even though your input is changing in a particular state, your output will not change with respect to your input asynchronously. It will only change when you come to a new state. Whereas in case of Mealy, this is the input then slash output. Your outputs are changing with respect to the state as well as with respect to the inputs. That is why you have lesser number of states here. For every states you can check that as soon as your inputs are changing, your outputs are changing. So outputs are determined by the inputs as well as the state. So if your state is not changing but your inputs are changing in that particular state, your output will change asynchronously. Next, we will understand what is the overlapping and non-overlapping cases for sequence detection. Let us say that I have a sequence 101. I have something like this. Uh, so let me just remove this sequence. Okay, so let us consider I have this pattern and I am supposed to detect sequence 101. In case of overlapping, what happens? Sorry, in case of non-overlapping, what happens? I have this sequence 101. I've detected the sequence. Then I'll forget about the sequence. I'll start my new sequence from here. Okay. So next I'll find next I will try to find 101 again. So I find my 101 here. So I have 101 occurring 2 times in this entire pattern. Whereas for overlapping case, I have my 101. I've detected my 101. I can leverage this one to detect the second sequence also. So my second sequence will start from the last bit of the previous sequence. So this is the first 101, this is the second 101, this is the third 101. So you have to be very careful in case of overlapping because you can make use of the last bit of the previous sequence as the first bit of your next sequence. So in case of overlapping, we have more detections as compared to the non-overlapping case. Now we will start with sequence detection FSMs for both these non-overlapping and overlapping cases, and we'll look at the Mealy and Moore in type FSMs in both these. So let us first discuss the non-overlapping case, and we'll check out Moore first, and our sequence is 101. So we always start with the reset state, or it is also known as the initial state, which is S0. And since previously we have looked at that in Moore, for every state you have output, and the output for this S0 state will be 0 because you have not yet detected the sequence. So from the reset state, this is S0 is a reset state, and in the reset state you start with, let's say, bit 1. So if you receive bit 1 and your starting bit is also 1 for your required sequence, so you proceed to a new state which is S1. The output is still 0 because you have not yet completely detected the sequence, and this is when you get a 1 from S1, S0 state. Whereas in case you get a 0 instead of 1, from S0 state if you get a 0, this means you cannot proceed with the sequence detection because the starting bit of your sequence itself is 1. So if you get a 0, you stay in the same state, you stay in the same initial state and you wait for the valid 1 to come. Okay. Next you have this S1 state with you. In S1 state we have looked at that from S0 if you receive a 1 you get to the S1 state. So in S1 state you already have a 1 with you. Okay, so in S1 state I already have a 1 with me, In case I get a 0 after this 1, if I get a 0, this means I can proceed to a new state S2, but my output is still 0 because I have not yet achieved 101. I have only achieved 10 till now. Whereas in case from S1, I already have 1 with me, and the next bit which I receive is also 1. What will I do? I'll discard this one. I'll consider this latest bit. I'll consider this latest received 1 as the starting of my new sequence. So the state at which you have 1 bit 1 is S1 state. In S1, I have 1 bit 1. So I'll remain in this S1 state. So in S1, I'll remain in this S1 state and I'll wait for my next valid bit to come. Okay, so from this S1 state, you're moving to S2 state when you're getting a 0, because you've already received 1 in S1 state. If you're getting a 0, you move to the S2 state. Whereas if you get a 1, you discard the previous one, you consider the latest one as your starting bit of your sequence, and you stay in the same state because this is the state where you receive 1 bit 1. Okay, now from this diagram, we can figure out that S2 is a state where you already have 1 0 present with you. So in S2 state, I already have 1 0 with me. If I get a 1, this means I have successfully detected my sequence. If I get a 1, I'll move to a sequence S3 and my output will be 1 because I've successfully detected my sequence. Whereas instead of 1, I already have 1 0 with me. Instead of 1, if I'm getting 0, this means no way I can proceed with the sequence detection because 0 was never the starting bit of your sequence 101. So what will you do? You will discard this entire thing. You will move to the reset state. If you get a 0 from your S2 state, you will move to the reset state. You will restart detecting the sequence and you will wait for your valid 1 to come so that you can proceed with the sequence detection. Now we will discuss S3 state. S3, we can figure out from the diagram that if you get a 101, you reach to the S3 state. So in S3, you already have 101 with you. So this is the S3 state. I already have 101 with me. In case I get a 0 after 101, then see, in case of non-overlapping, we have previously looked at that once you detect your first sequence, you cannot leverage the last bit of your previous sequence as the first bit of your next sequence. So this one cannot be leveraged from your previous sequence to detect a new sequence because this is a non-overlapping case. So this will change in case of overlapping, which we will look later in the video. But for now, just remember that this is a non-overlapping case and this one is of no use to me. So since I've received 0 here, my sequence is broken because the starting bit of my sequence is 1. So what will I do? I will restart. I'll move to the reset state. I'll move to this reset state and I'll restart the sequence detection. I'll wait for my next valid 1 to come. Whereas in S3 state, you have 101 with you and instead of a 0, you're getting 1. So previously also we have said that this is of no use, but the starting bit is 1 for my required sequence because I need to detect 101. So this one can be of use to me because this one can act as a starting point of my next sequence. So I'll move to a state where I have 1 bit 1 with me, which is the state where I have 1 bit 1 with me. That is the S1 state. In S1 state is a state where you receive the first bit, the first bit of the sequence or one of the sequence, the first one of the sequence. So from S3 state, if you're getting a 1 after S3, you move to the state S1 if you receive a 1. So I hope this sequence detection was clear. Next, we'll discuss the Mealy type. Now let us discuss the Mealy type FSM. So Mealy type FSM for a non-overlapping case and your sequence is 101. So similar to your move type, you start from your reset state, which is S0. And since this is a Mealy type FSM, your states won't determine your outputs, instead your inputs will. So if you get a 1 in your from your reset state, your output is 0 because your sequence has not yet been detected, but it will move to a new state S1. So your S0 is the reset state, and from your reset state, if your first bit is 1, this means you can proceed with the sequence detection. You're good to go to the next state. In case you're getting a 0, this means you remain in the same state and you wait for the first valid bit, that is 1, to come so that you can proceed with the sequence detection. Now we'll discuss state 1. In state 1, you already have a 1 with you. After this 1, if you're getting a 0, this means your sequence detection is closer. So you move to a new state, which is S2, and your output in this case is still 0 because you have not yet completely detected the sequence. You have only reached till 1, 0. So from S1, if you're getting a 0, you're good to go for the sequence detection. You move to the new state. But in case from S1, you already have a 1 and you get the next bit as 1. This means you can discard the previous bit. You can start the sequence detection from the latest bit, which is 1. So this will act as the first bit of your sequence. And I know that the state which represents the first bit, the first received bit, uh, 1 is your state S1. So if you have 1 with you, your output is still 0, but you remain in the state S1 to receive your next valid bit, which is 0. So for ease of understanding, I'll write here S0 is your reset state, S1 is the state where you have received your 1, S2 is the state where you have received 1, 0. Now we'll move on to your state S2. In S2, I already have 1, 0 with me. Okay, so if I get 1, 0, I already have 1, 0, and if my next bit which I get is 1, if the next bit which I get is 1, this means my sequence detection has successfully completed and I can move on to the reset state to start with the new sequence. If I get a 1, this means I have detected the sequence. I can move on to the next sequence to be detected. So I move on to the reset state if I get a 1, and the output will be 1 because 101 is detected. I already have 10 here. I get a 1, my sequence is detected, my output is 1. So you go to the reset state where you are getting ready for the next sequence to be detected. What if instead of 1 you're getting the input bit as 0? You already have 10 with you, but instead of 1 you're getting a 0 here. This means you cannot proceed further. You discard everything. You move to the reset state to get the next valid bit, because there is no way you can proceed with this 0 for the sequence detection. So if you're getting a 0, your output is still 0 because the sequence is not yet detected. You move to the reset state so that you wait for the next valid bit, which is 1. So this was a case for non-overlapping Mealy type machine, and we can see from the previous example in this that the number of states reduces in Mealy because your input is one of the deciding factors for your the inputs are also one of the deciding factors for your outputs along with the states. So you have lesser number of states here, whereas in the previous case for every state there was one output. So the number of states increases in Moore. Next we'll discuss the overlapping cases for 101 and Mealy and Moore type FSM. So now let us discuss the second part of the sequence detection, which is your overlapping case. And in this overlapping, we again have two types, which is Moore type FSM and your Mealy type FSM. So let us start with Moore type FSM for 101 sequence detection. So we all know in previous cases we have started with your reset state, which is S0, and since this is Moore type, every state will have an output and S0 will have an output of 0 because your sequence detection is not yet completed. Okay, so in this S0 state, this is nothing but your reset state, and we'll start the sequence detection here. So let us say that the first bit which you get is 0. Since this is 0 and my starting bit of my required sequence is 1, I cannot proceed with the sequence detection. So I'll stay in the same state and I will wait for the valid bit, which is my 1. Now if you get 1, then you move to a new state, which is S1, and the output will still be 0 because you have not yet detected the sequence. So my S1 state is a state where I get 1. Okay, so now let us figure out what will be the transitions from S1 state. In S1 state, you already have 1 with you, and after this 1, if you get another 0, this means you're closer to detecting the required sequence. So you move to a new state, which is S2, and the output is still 0 because the sequence is not yet completed. Okay, but instead of getting you're receiving this second bit as 0, if you're receiving the second bit as 1, this means you can ignore this one. You can start your sequence detection with this latest one, and that means you will stay in the same state and you will wait for the second valid bit, which is 0, so that you can proceed with the sequence detection. So S1 is a state where you get 1 bit 1. So, and here if I look at my case where I get the second bit as 1, this one is of no use now, and and I have 1 bit 1 with me. So the state at which there is 1 bit 1, the state at which we have 1 bit 1 is your S1 state. So we'll remain at S1 state. We'll wait for the next valid bit to come, which is my 0, to proceed with the sequence detection. Now let us say you have state S2. So in state S2, what do we have? In state S2, we already have 1, 0 with us. So, and if I get another 1 after from this S2 state, then I have completed my sequence detection. So I'll move to a new state. If I get another 1 from S2 state, I'll move to a new state S3, and my output will be 1 because I've completed successfully detected my sequence. Whereas if from S2 state you already have 1, 0 with you, and instead of getting a 1, if you're getting a 0, then what happens? Your entire sequence continuity is broken. You discard everything. You restart from the reset state if you get a 0, because 1, 0, 0. These three are of no use because you cannot proceed with the sequence detection. So the sequence is 1, 0, 1. Your first bit should be 1. So you move to the reset state if you get a 0 from S2 state, and then you wait for the valid bit to come, that is your 1. Now we will check out the S3 state. In S3 state, if let us say in S3 state you have you are getting a 1, your S3 state is the state where you already have 101 with you. Now in S3 state I already have 101, and the next bit which I get is 1. So what happens? I can start my new sequence with this one. I don't need anything from my previous sequence. Why am I saying that I might need something from my previous sequence? Because this is a overlapping case. You can leverage those previous bits in order to continue with the new sequence detection. But since in our non-overlapping cases, we have seen that as soon as a sequence is detected, this plays no role. Any of the bits from this sequence plays no role in the second sequence detection. You just forget about this sequence detection once it is detected in case of non-overlapping. But in case of overlapping, you can leverage this last bit of your sequence to continue with a new sequence. Okay. So since this is since the new bit that you incur is 1, I can simply start my new sequence with this latest bit 1, and I know a state where you get 1 bit 1, which is that state S1. S1 is the state where you get 1 bit 1. So you move from S3 to your S1 state in case you get 1 after detecting the sequence. Whereas you already have 101 with you and you are getting a 0, then what happens? We know this is an overlapping case. Overlapping case means you can leverage the last bit of your previous sequence. So I'm leveraging this last bit 1, and this I have my latest bit is 0. This means I have 1, 0 with me. I just need the third bit. So the state where you already have 1, 0 with you is S2. So you move to your S2 state in case you get a 0. So I hope this was clear. So this was a Moore type machine, and in Moore type machine we have seen the number of states increases because the outputs are determined by your state and not by your inputs. Now we will move to your second case, which is your Mealy type. So this is the overlapping case for Mealy, and you are required to detect your same sequence, which is 101. So similar to the previous case, we start with a reset state, and if you get a 1, you proceed to a new state S1, and the output is still 0 here because you have not yet detected the sequence. In case you get a 0 in the reset state, you stay in the same state and you wait for the valid bit, which is 1. And your output here is also 0 because you have not yet detected the sequence. So S0 is your reset state, S1 is the state where you get 1, 1. Next, from S1 state, if you get in S1 you already have a 1. If you get a 0, you move to a new state S2, and your output is still 0 because you have not yet detected the sequence. Whereas if you get 1, you stay in the same state and still the output is 0. So you already have 1 with you, and instead of getting a 0 you get a 1. You discard this 1. You consider this 1 to be the starting of your sequence. So you stay in the same state and you wait for the next valid bit, because you know that the state in which I have 1 with me is your S1 state. Now we will look at the S2 state. In S2 state, I already have 1 0 with me. In S2 state, I already have 1 0 with me. So in order to detect the sequence, I need another 1. So after this 1 0, if I get a 1, this means I have detected my sequence, and I can, the most important part comes here, because see, once you get a 1 here, your sequence is successfully detected. But since this is an overlapping case, I can leverage this one as the starting of my next new sequence. Okay, so this one should be considered as the first bit of your second sequence also. So this last bit is the last bit of your previous sequence, plus this is the first bit of your next sequence. And this is possible because this is an overlapping case. You can leverage the last bit of your previous sequence. So the state where you already have a 1 with you, 1 bit 1 is your S1 state. So in case I get a 1, I move to state S1. In case I'm getting a 1, from in S2 state I already had 1 0. If I'm getting a 1, this means my sequence detection has completed. I've successfully detected my sequence, so my output will be 1. Okay, but you're moving to your S1 state instead of the reset state, because in your non-overlapping case you used to move to the reset state, because as soon as your sequence detection is completed, you don't have anything to do with your previous sequence. But since this is an overlapping case, your previous sequence can be used to continue with the sequence detection of your next sequence can be detected. So what happens? You move to a state where you already have 1 with you, and that is your S1 state. In case from S2 state, I already have 1 0 with me. Instead of 1, I'm getting a 0. No way I can proceed with the sequence. I discard everything. I move to the reset state to get the valid bit. And your output is 0 here because the sequence is not yet detected. So always compare your Mealy overlapping with your Mealy non-overlapping and Moore overlapping with your Moore non-overlapping to get a better understanding. So I hope this sequence detection was clear for all the 4 cases. In case of any questions, you can please comment down below. So I'll reply to them within 24 hours. Thanks a lot.